Hey students, I thought I'd put together a little supplemental lecture video. We did chapter 1 on things like unit conversion and significant figures. And I wanted to do a few examples in class and got a chance to do a few. But my plan was to do a few more from the book, and we just ran out of time. So if the lecture made sense, you probably don't even need this. Go ahead and get started on the homework. But before Zoom time started, I thought I would add the 3 examples that was my plan to be part of the lecture. So I'll just kind of add that to the video material today, and you can decide how much or how little of this you want to watch. But these are really good examples. And so let me read number 4. It's very similar to one of the homework problems you have, which is right next to it, number 5. But it says here, an American football is played on a 100-yard long field, excluding the end zones, period. Okay, how long is the field in meters? And then they can say, go ahead and assume that 1 meter equals 3.281 feet. All right, so here was the lesson I was trying to say. If you take here 100 yards, the idea of the unit conversion is to switch it into something that gets you in the direction of where you wanted to go, maybe not all in one step, but in this case, I'd like to get rid of yards, so I'm going to put yards down here and convert it into meters. Now, they did not tell me how many meters are in a yard, but they did tell how many meters or how many feet were in a meter. So why don't I do this? Why don't I do a unit conversion that is going to cancel out what I want to get rid of, yards. Remember, yards down here. And then convert it into feet. And as I was trying to emphasize in the lecture, the trick here is to multiply it by a fancy 1. So you really don't change the total distance of 100 yards. You just have a different number and a different unit, but it still means the same thing, sort of like taking the number 12, which would be 6 times 2, but now changing it into something like 4 times 3. So you change both of those, but the product is still the same. And that's what we're going to do. We're going to change the number 100, and we're going to change the unit yards into something else. Now, this first step would change it into feet. And so you know that 3 feet is in 1 yard. Okay. And then, of course, by the way, we also want to watch our significant figures here. But in this case, I would say a football field is designed to be, by definition, exactly 100 yards. So there's an infinite number of significant figures. And again, by definition, 1, so this is exactly 1, so there's an infinite number of significant figures, is designed to be exactly 3 feet. So again, this number 3 is not a 3 and a little bit. It's not a measured value. It is actually a mathematical number 3. So all of these have an infinite number of significant figures. So keep that in mind. And so this comes out to be 300 feet. And you probably really didn't need to go to too many steps to kind of figure that out, that 100 yards is 300 feet, because this factor of 3 is pretty simple. But that was my design. So again, this is just multiplying by 1. Now I can say, let's get rid of feet and switch it into something we do know, and this is our ultimate step into the number of meters. And they give this. They say 1 meter, so exactly 1 meter, is equal to 3.281 feet. Okay, and of course, this is kind of the demonstration I was trying to show you. When you're converting units, you know, you put downstairs the one you want to get rid of, feet, and upstairs you put the one you want to convert it to. Now, sometimes it takes a couple steps to get there. So I ultimately wanted to get to meters, and I couldn't do that in one step because I didn't know how many meters were in a yard, although I guess I could have looked that up. But I needed to given this, I think they wanted me to do this. So this is common knowledge, and this is what they gave us. So again, switching yards into feet, and now feet into meters. And so if you look at the units, you're going to come out here into meters. Now, with that said, I should probably ask about significant figures here. And as we said, the 300 is really an infinite number. And this is exactly 1 meter. So this is 1.00000. So this is an exact number too. So that's another infinite. Now here's where we don't have an exact infinite. This is saying that 1 meter is 3.281. And there's probably another number here, but we just don't know what it is. So that's an unknown number. That's a measured value here. Or maybe it could be even a calculated value, but we just don't know what the other decimals are. But in either case, it looks like we know 4. We don't know the 5. So the limiting number is 4 significant figures, because infinite, infinite, and 4. So we should have 4 in our answer. So let me take 300 and divide it by 3.281, and I would get 91.4, and it looks like that would round to a 4. And I don't have to put question mark, but that's what I was doing in the lecture to say, look, this is our way of indicating that we know this number is a 4, but we don't know the next number. And so that's your sig figs, your significant figures. And there's your conversion. And in this case, took 2 steps. All right, let me try another example here. And again, hopefully you'll kind of see that same thing. It says here on number 24, a marathon runner completes the 188 kilometer course in 2 hours and 30 minutes and 12 seconds. There is an uncertainty of about 25 meters in the distance traveled, and there is an uncertainty of about 1 second in the time. Calculate the percent uncertainty in distance, and then B, calculate the uncertainty of the elapsed time. C, what is the average speed in meters per second, and D, what is the uncertainty of this average speed. Now, I really wanted to do this one because this was my example of talking about uncertainties instead of just sig figs. But I'll just say that I guess I did say that I wasn't going to be able to have enough time to cover everything in Chapter 1, but it's pretty straightforward, and uncertainty is one of them. But I wanted to make this extra video really for this purpose here, because I want you to kind of see something here. If I was showing you in the lecture, if I was to multiply something together, like A times B, of course, I would get AB. But another way of labeling our uncertainties is instead of having sig figs, we do something like this. We say A plus and minus a little bit. So I'll call it delta A. And then maybe B plus or minus delta B. And I'll multiply them together in a minute here. But see, this right here is the uncertainty. So when they say that it is 42.188 kilometers plus or minus, and they say the uncertainty is 25 meters. So that means every marathon course varies a little bit by 25 meters. Some are 25 meters further than the other. They don't measure them exactly. In fact, remember, you could never do it exactly, but you could get closer than 25 meters. You could say within 1 meter would be very reasonable, or even within 1/10 of a meter, so that roughly it's the same. But I suppose the 25 meters is a good number because you have a start of a race, you have so many people lined up that there's a plus or minus 25 meters right there. Although my friend who runs marathons, I've noticed, seriously, they got an interesting configuration. And when the gun goes off, he's got a little timer, and sometimes it's on his wrist, sometimes it's on his ankle. He prefers it on his wrist so he's not carrying the weight. But the timer will go off when the gun goes off, and then there's a second timer that activates when he crosses the start line. So he's back a little bit. You know, he's not like one of these professional runners, but he's back a little bit, and they when he starts there, it'll start clicking. So a lot of times there'll be a 2 or 3 minute delay by the time he gets the chance to really start the race. And so he has 2 times when he finishes, the time on the course and the time on the track or the path. Anyways, I digress a little bit, but this is what we really have. We have an uncertainty, and this is called the uncertainty. And so usually the uncertainty, and so let me make these match a little better. I'm going to change it to meters here. And so I'll just go 42.188. And as I was saying in class, you can think of the kilo as 1,000. This makes the unit conversion a little bit easier than doing something kind of long-winded like this. And then just take the number, so the kilo means 1,000, and multiply it by here, so that makes 42,188 meters, plus or minus 25. So this often is a better way of writing it when the uncertainty is within these. So these are technically significant figs, but, well, they're technically digits, but they're really not significant, and this is how we would indicate that. And so there is significant figures where you trust that number, and then there's this kind of thing where this is a rough number and then plus or minus. And so this 8, both these 8s are in the same category as this one. So I would say these are not well known. They're only partially known, this much. Okay, and so that's how you might indicate it. So writing things as an uncertainty is actually really nice, and I kind of feel bad now for not having the time to kind of emphasize that sometimes we write things with uncertainties and sometimes we write them with sig figs. And we're trying to do the same thing. We're trying to say how much we trust the number, but this gives us more play with how we can say we trust that number. It doesn't have to be a whole digit and a factor of 10. And it also doesn't have to be something smaller than the last one. And so there's a real nice advantage of uncertainties. And like I said, just feel a little bad I didn't get a chance really to talk about that. But I guess that's what I'm doing this now for. Okay, so this is what we mean by the uncertainty. Now, well, let me come back up to the question, because the question A says calculate the percent uncertainty. So this is the actual distance. A percentage then would be a part over the whole. And so maybe I need to take you back to your algebra class. And when you do percentages, they look like this. You say what part out of the whole, and so that's your fraction, and then multiply by 100 to make it into a percent. And so in case you've forgotten your percentages, this is why, like I said, would be a real good one for me to do here. All right. So here is then the percent uncertainty. So if I take the 25 and divide it by the 42,188, I'd call that my fraction uncertainty, plus then 100, and it's still a small percentage, but it would be 0.059%. So another way of writing this uncertainty would be to say, I know the distance of the marathon is 42,188 plus or minus 0.059%. And so we can write the uncertainty as either a percentage or as an absolute number. And they both have their advantages. And we'll get to that in this problem. But right now, they wanted us to basically change the absolute uncertainty into a percentage uncertainty. And so that's the answer to A. Calculate the percent uncertainty in the distance. Now B, I think, is kind of that same thing. It says calculate the percent uncertainty, calculate the uncertainty in the elapsed time. Okay, so the elapsed time is 2 hours, 30 minutes, 12 seconds, and then plus or minus 1 second. Now, it probably makes sense to write this in the same units. So let me start with 2 hours. So 2 hours Now, if I multiply that by 60, that's how many minutes. And if I multiply that by another 60, that's how many seconds. So I'll just put up here, this is 7,200 seconds. Now, the 30 minutes would be the 30 times another 60, so that's 1,800 seconds, and then 12. So let me just come up here and grab the 7,200. Let me also grab the 1,800, so I can do some copy and paste. And let me add then the 12. And so a better way of writing this is 9,012 seconds plus or minus 1 second. And this is what we'd call the absolute uncertainty. But they're asking for the percentage. So the percentage would be part over the whole multiplied by 100. So 1 divided by my last answer multiplied by 100 means we have about a 0.011 percentage. There's no units there. So we could write this as 9,012 seconds plus or minus 0.011. And so I want to emphasize this is saying the same thing. This is the percentage of that number. This is the absolute. And we are asked for the percentage. That was B. I'll read it again. Calculate the uncertainty in the elapsed time. Now, here's what's kind of interesting and what I wish I had time in the lecture to show you. It says, what is the, oh, I guess it's D. So, but anyway, let's go on to what is the average speed in meters per second. And I got to admit, that might be a little bit of an unfair question because we don't really talk about average speed until the next chapter. I think the author's kind of relying on you to have a little bit of background in physics or maybe just math where you know the word speed and average would be the whole distance over the whole time. And maybe that's why they made it its own little problem, just to kind of make you think, okay, now what is average speed again? So my average speed would be the distance, the 42,188 meters. Back here. This first page, there it is, 42,188 meters. There's the absolute uncertainty. There's the percent uncertainty. And then the time is the 9,012 seconds. So without worrying about any uncertainties yet, I would just take 42,188 divided by 9,012 and come up with 4 points. And maybe at this point I'll just talk about significant figures, like these are valuable. Remember, they're not really because I got an uncertainty. But let me just call that 5 and that 4. And so let me finish with 4 here. And the units would be meters per second. So the average speed is 7 meters per second for this person running a marathon. And at a pretty good pace, 2.5 hours is, well, I would say anything sub 3 is a good race. Like I said, my buddy went sub 3. That was a big deal. And if he could get down to 2:30, that would be an awesome. But I don't think it's in the cards for him. If marathon runners do peak late in life, it takes years to build up. But he's past that, so I don't think his time's going to go lower. Maybe, but probably higher. Anyways, I'm chit-chatting again here. So anyways, this is the average. But there would be this plus or minus. And that's ultimately what I want to get to, which is D, which says, what is the uncertainty in this average speed? Which takes me all the way back to right here. So you can kind of see the proof. If you were to multiply this out, maybe you remember a technique you learned called FOIL, but you would multiply the first two together. That would be A times B. Then you would have these two, which I guess would be plus or minus the uncertainty of A times B, and then plus or minus the uncertainty of B times A, and then finally the uncertainty of A times the uncertainty of B. And this is kind of my little proof. If we divide everything to make it a percentage, you'll see something quite interesting here. This right here is just 1. So that's really your answer. You know, what percentage of an answer do you get, A and B, when you divide by A and B? So this is your 100%. And then watch this, plus or minus. The B would cancel off, and so this is your fractional error or percent error in A. And this over here, where the A's would cancel off, would be your fraction in B. And so this is saying your plus or minus would be your percent error of A, and then added to your percent error in B. And that's what I wanted to show you. How do you calculate the uncertainty when you do something like a multiplication or division? And the answer is you add the uncertainties. Now, just for completeness, I'm just going to drop this because this is actually the product of the two uncertainties. And if your uncertainties are small, like in our case, let's see, what would we have? A 0.01% here and 0.05. When you multiply those percentage together, they're so small we can neglect them. And so we only have to worry about adding the two together. If you want to be a little more accurate, you would take the product of the two and add that. But that's going to be, 100 times smaller than these. And so it's really kind of irrelevant. And so that's what I'm going to do, is just add the uncertainties. So here's what my answer would come out to be. It'd be 4.681 plus or minus, and I would have the uncertainty from the distance, 0.059%, and then plus or minus the uncertainty from the time. And so since I'm doing a quotient, my uncertainty is a combination of both. It's a combination of the uncertainty in the distance and the uncertainty in the time, and the way you get the uncertainty in your answer. And so notice every time I do a multiplication or division, my answer gets less accurate. I keep adding percent errors together. And in this case, looks like, let's see, that 5 and that 1 makes 6, and this is a 7, so it'll be 0.070%. So again, not a whole lot, but notice that the answer here has more of a percent error than the individual pieces that make it up. And most of the uncertainty, most of the error comes in measuring the distance. This is about 6 times bigger than that one. And so about 0.06 is from the unknown in the distance, and the other 0.01 is from the unknown in the time. But then this number is unknown by 0.07, the sum of the two. So I hope I didn't talk too much on that one, but that was the big one that I really wanted you to see, why I was motivated to do this supplemental video, because I didn't get to it in class, and it is time to move forward. Well, I want to do another one here. And so let's look at 29. And then I think it'll almost be Zoom time, and so I'll have to post this a little bit later. But I only got a chance to do one approximation one. And again, this goes almost without saying. So usually students don't have too hard of a time. The answer is, try to answer the question based upon information given or what you know to the best of your ability. Some approximations are actually pretty good because we know a lot of information, and other ones are just ballpark, what we call order of magnitude. And so we just know it's more than 10, less than 100. We go, okay. Within a factor of 10, it's probably a 10. It's not 100, and it's not a 1, but it's a 10. Anyways, and I can do a little better on this one, because this one says about how many heartbeats are there in a lifetime. Okay, so maybe I will start with something that I I kind of know, and that is maybe you have about 70, I'm going to go call it 72 beats per minute. So now I just need to multiply by the number of minutes that a person is alive. And that might be a little bit high for resting, but definitely high for resting, depending on your age. Maybe I'd feel better since it's an estimate. 70 looks like one significant figure. So let me call it 70. So I'm going to say there's about 70 beats per minute of your heart. And then I need to know how many minutes. That'll give me my total over a lifetime. But why don't we just do that? What is a lifetime? This is a nice unit conversion. I think the average expected lifespan is about 78 years now. So if we multiply that by 365, I suppose we could even put a leap year, because by the time you average over a lifetime, you get that extra leap day every 4 years. So maybe I should say there are 365 days in a year. And I apologize, I should have done the units first. I want to get years to cancel off and get left with days. Then maybe I would want to get rid of days, and to do that, I know that there's hours. So maybe I'll put 24 hours in a day. I'm going to run out of room, so I'm going to come down here. Because I'd like to get rid of hours, and I know how many minutes then. There are 60 minutes in 1 hour, and so the hours would cancel off. Oh, and day, I forgot to cancel it off. But if you look at that, I changed years into days, and then days into hours, and then hours into minutes. So that's what I was kind of hunting for, about how many minutes represents a lifetime. So this is kind of a unit conversion. So here's 78 times 365 and a quarter. Notice the significant figures wouldn't even matter once we ultimately did it, so a quarter is kind of irrelevant. And this is just more accurate than that one. Times 24 times 60. And maybe I'll just write down 4, 1, and stop for a moment and ask, well, how many significant figures do I have? Looks like this is probably 2, and I don't even know if they're significant. I'm kind of guessing here. But let's call it 2. This looks like 5. That looks like infinite because exactly 1 year. That's 24 exactly, so that's an infinite of 1 day. That's infinite. 60 minutes, yeah, exactly. So that's an infinite number in 1 hour. 1 exactly, yeah. So infinite. So infinite, 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 5, and 2. So my limiting factor would be 2. So 4.1 times 10, 1, 2, 3, 4, 5, 6, 7 minutes. So finally now I can answer this approximation question by saying, all right, I've got 70 beats in a minute. And over a lifetime, 4.1 times 10 to the 7th, which I can think of this as 41 times 10 to the 6th. So 41 million minutes is a typical lifetime. Okay. So 70 times, and I'm just going to go ahead and take that last answer, even though there's a little more digits that aren't significant, but I won't even write those down. I will go with 2 significant figures and call it 2.9 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9 beats. Which is quite a bit. About 3 billion beats. And so a typical person, it's amazing how long the heart lasts. It's a good thing that the living tissue keeps regenerating, because I don't think you could start with something at birth and let it beat for 3 billion times without some kind of maintenance or improvement, or in this case, redevelopment of of the muscle walls and the muscle cells in order to make them stronger. So we got to keep the machine going. All right, well, I about hit my half hour, and so I'm going to call it quits and Zoom with you guys in about 15 minutes if anybody pops in. Otherwise, I'll do some other solutions from the homework, but hopefully the supplement problem solving will be useful to somebody. Take care.